Tantor Audio, a division of recorded books, presents The Emperor's New Mind, Concerning Computers, Minds and the Laws of Physics, by Roger Penrose. Narrated by Julian Alpha. Foreword by Martin Gardner. Many great mathematicians and physicists find it difficult, if not impossible, to write a book that non-professionals can understand. Until this year, one might have supposed that Roger Penrose, one of the world's most knowledgeable and creative mathematical physicists, belonged to such a class. Those of us who had read his non-technical articles and lectures knew better. Even so, it came as a delightful surprise to find that Penrose had taken time off from his labours to produce a marvellous book for informed laymen. It is a book that I believe will become a classic. Although Penrose's chapters range widely over relativity theory, quantum mechanics, and cosmology, their central concern is what philosophers call the mind-body problem. For decades now, the proponents of strong AI, artificial intelligence, have tried to persuade us that it is only a matter of a century or two, some have lowered the time to 50 years, until electronic computers will be doing everything a human mind can do. Stimulated by science fiction read in their youth and convinced that our minds are simply computers made of meat, as Marvin Minsky once put it, they take for granted that pleasure and pain, the appreciation of beauty and humor, consciousness and free will are capacities that will emerge naturally when electronic robots become sufficiently complex in their algorithmic behavior. Some philosophers of science, notably John Searle, whose notorious Chinese room thought experiment is discussed in depth by Penrose, strongly disagree. To them, a computer is not essentially different from mechanical calculators that operate with wheels, levers, or anything that transmits signals. One can base a computer on rolling marbles or water moving through pipes. Because electricity travels through wires faster than other forms of energy, except light, it can twiddle symbols more rapidly than mechanical calculators and therefore handle tasks of enormous complexity. But does an electrical computer understand what it is doing in a way that is superior to the understanding of an abacus? Computers now play grandmaster chess. Do they understand the game any better than a tic-tac-toe machine that a group of computer hackers once constructed with Tinker Toys? Penrose's book is the most powerful attack yet written on strong AI. Objections have been raised in past centuries to the reductionist claim that a mind is a machine operated by known laws of physics, but Penrose's offensive is more persuasive because it draws on information not available to earlier writers. The book reveals Penrose to be more than a mathematical physicist. He is also a philosopher of first rank, unafraid to grapple with problems that contemporary philosophers tend to dismiss as meaningless. Penrose also has the courage to affirm, contrary to a growing denial by a small group of physicists, a robust realism. Not only is the universe out there, but mathematical truth also has its own mysterious independence and timelessness. Like Newton and Einstein, Penrose has a profound sense of humility and awe toward both the physical world and the Platonic realm of pure mathematics. The distinguished number theorist Paul Erdős likes to speak of God's book, in which all the best proofs are recorded. Mathematicians are occasionally allowed to glimpse part of a page. When a physicist or a mathematician experiences a sudden aha insight, Penrose believes it is more than just something conjured up by complicated calculation. It is mind making contact for a moment with objective truth. Could it be, he wonders, that Plato's world and the physical world, which physicists have now dissolved into mathematics, are really one and the same? Many pages in Penrose's book are devoted to a famous fractal-like structure called the Mandelbrot set, after Benoit Mandelbrot, who discovered it. Although self-similar in a statistical sense, as portions of it are enlarged, its infinitely convoluted pattern keeps changing in unpredictable ways. Penrose finds it incomprehensible, as do I, that anyone could suppose that this exotic structure is not as much out there as Mount Everest is, subject to exploration in the way a jungle is explored. Penrose is one of an increasingly large band of physicists who think Einstein was not being stubborn or muddle-headed when he said his little finger told him that quantum mechanics is incomplete. To support this contention, Penrose takes you on a dazzling tour that covers such topics as complex numbers, Turing machines, complexity theory, the bewildering paradoxes of quantum mechanics, formal systems, Godel undecidability, phase spaces, Hilbert spaces, black holes, white holes, Hawking radiation, entropy, the structure of the brain, and scores of other topics at the heart of current speculations. Are dogs and cats conscious of themselves? Is it possible in theory for a matter transmission machine to translocate a person from here to there the way astronauts are beamed up and down in television's Star Trek series? What is the survival value that evolution found in producing consciousness? Is there a level beyond quantum mechanics in which the direction of time and the distinction between right and left are firmly embedded? Are the laws of quantum mechanics, perhaps even deeper laws, essential for the operation of a mind? To the last two questions, Penrose answers yes. His famous theory of twistors, abstract geometrical objects which operate in a higher dimensional complex space that underlies space, time, is too technical for inclusion in this book. They are Penrose's efforts over 2 decades to probe a region deeper than the fields and particles of quantum mechanics. In his fourfold classification of theories as superb, useful, tentative, and misguided, Penrose modestly puts twistor theory in the tentative class, along with superstrings and other grand unification schemes now hotly debated. Since 1973, Penrose has been the Rouse Ball Professor of Mathematics at Oxford University. The title is appropriate because W. W. Rouse Ball not only was a noted mathematician, he was also an amateur magician with such an ardent interest in recreational mathematics that he wrote the classic English work on this field, Mathematical Recreations and Essays. Penrose shares Ball's enthusiasm for play. In his youth, he discovered an impossible object called a tribar. An impossible object is a drawing of a solid figure that cannot exist because it embodies self-contradictory elements. He and his father Lionel, a geneticist, turned the tribar into the Penrose staircase, a structure that Moritz Escher used in 2 well-known lithographs, Ascending and Descending and Waterfall. One day when Penrose was lying in bed in what he called a fit of madness, he visualized an impossible object in 4-dimensional space. It is something, he said, that a 4-space creature, if it came upon it, would exclaim, "My God, what's that?" During the 1960s, when Penrose worked on cosmology with his friend Stephen Hawking, he made what is perhaps his best-known discovery. If relativity theory holds all the way down, there must be a singularity in every black hole where the laws of physics no longer apply. Even this achievement has been eclipsed in recent years by Penrose's construction of 2 shapes that tile the plane in the manner of an Escher tessellation, but which can tile it only in a non-periodic way. Penrose invented them, or rather discovered them, without any expectation they would be useful. To everybody's astonishment, it turned out that 3-dimensional forms of his tiles may underlie a strange new kind of matter. Studying these quasicrystals is now one of the most active research areas in crystallography. It is also the most dramatic instance in modern times of how playful mathematics can have unanticipated applications. Penrose's achievements in mathematics and physics, and I have touched on only a small fraction, spring from a lifelong sense of wonder toward the mystery and beauty of being. His little finger tells him that the human mind is more than just a collection of tiny wires and switches. The Adam of his prologue and epilogue is partly a symbol of the dawn of consciousness in the slow evolution of sentient life. To me, he is also Penrose, the child sitting in the 3rd row, a distance back from the leaders of AI, who dares to suggest that the emperors of strong AI have no clothes. Many of Penrose's opinions are infused with humor, but this one is no laughing matter. Preface. The Emperor's New Mind, published in its original form in 1989, represents my first serious venture into popular science writing. As part of the aim of this book, I try to set forth, as clearly as I can, a good deal of the profound progress that physicists have made towards an understanding of the workings of the physical world. But this is not simply a piece of scientific exposition. I also try to point out some of the important ways in which our present scientific understanding still falls a long way short of its ultimate goal. Most particularly, I argue that the phenomenon of consciousness cannot be accommodated within the framework of present-day physical theory. This runs contrary to a certain common perception of the implications of a scientific viewpoint. According to this perception, all aspects of mentality, including conscious awareness, are merely features of the computational activity of the brain. Consequently, electronic computers should also be capable of consciousness and would conjure up this quality as soon as they acquire sufficient computational power and are programmed in an appropriate way. I do my best to express, in a dispassionate way, my scientific reasons for disbelieving this perception, arguing that the conscious aspects of our minds are not explicable in computational terms, and moreover, that conscious minds can find no home within our present-day scientific worldview. Nevertheless, it is not my contention that we should look outside science for an understanding of mentality, merely that existing science has not the richness to achieve what is required. One thing that I had not adequately anticipated while writing this book was the vehemence that my thesis would evoke, mainly from those who strongly support the computational model of the mind, but also from some who regarded science as anathema to the study of consciousness. No doubt a person's philosophical position with regard to the mind can, like a person's religion, be a touchy subject, but just how touchy a subject it can be was not something that I had fully appreciated. My reasoning, as presented in this book, has two main strands to it. The first of these endeavours to show, by appealing to results of Godel and Turing, that mathematical thinking, and hence conscious thinking generally, is something that cannot be encapsulated within any purely computational model of thought. This is the part of my argument that my critics have most frequently taken issue with. The second strand of the reasoning is to demonstrate that there is an important gap in our physical picture of the world, at a level which ought to bridge the sub-microscopic world of quantum physics to the macro world of classical physics. My viewpoint demands that the missing physics falling within this gap, when found, will play an essential part in the physical understanding of the conscious mind. Moreover, there must be something outside purely computational action in this sought-for area of physics. In the roughly 10 years that have elapsed since the first printing of this book, there have been a number of clear-cut developments, and I wish to give an outline of some of these here, so that one can gain some understanding of what I perceive to be the present status of these ideas. To begin with, let us consider the status of the relevance of Gödel's theorem in relation to some of the criticisms that my argument stirred up. What Gödel's theorem tells us, in a nutshell, is the following, which is not controversial. Suppose that we are given some computational procedure, P, for establishing mathematical assertions, let us say assertions of a particularly well-defined type, such as the famous Fermat's last theorem. Then, if we are prepared to accept that the rules of P are trustworthy, in the sense that we accept that the successful derivation of some mathematical assertion by use of the rules of P provides us with an unassailable demonstration of the truth of that assertion, then we must also accept as unassailably true some other assertion, G open parenthesis P close parenthesis, which is beyond the scope of the rules of P. Thus, once we have seen how to mechanize some part of our mathematical understanding, into P, say, then we can also see how to transcend this mechanization. To me, this provides a clear-cut reason for believing that our mathematical understanding contains elements that lie beyond purely computational action. But many critics have remained unconvinced and have pointed to various possible loopholes in this deduction. In my follow-up book, Shadows of the Mind, I responded to all these criticisms in some detail and provided a number of new arguments to counter these criticisms. However, the argument still goes on. One of the reasons that people sometimes have difficulty in seeing the relevance of Gödel's theorem to our mathematical understanding is that, according to the way in which the theorem is usually presented, G open parenthesis P close parenthesis seems to have little relevance to any mathematical result of interest. Moreover, G open parenthesis P close parenthesis as a mathematical statement would be enormously difficult to comprehend. Accordingly, even mathematicians often find themselves happy to disregard mathematical statements like G open parenthesis P close parenthesis. Yet there are examples of Gödel's statements that are easily accessible even to those who have no particular familiarity with mathematical terminology nor notation beyond that which is used in ordinary arithmetic. A particularly striking such example came to my attention only after the aforementioned writings were published. This is the result known as Goodstein's theorem. I believe that it is instructive to give Goodstein's theorem explicitly here, so that one can gain some direct experience of a Gödel-type theorem. To appreciate what Goodstein's theorem asserts, consider any positive whole number, let us say 581. First, we express this as a sum of distinct powers of 2. 581 equals 2 to the power of 9 plus 2 to the power of 6 plus 2 to the power of 2 plus 1. This is what would be involved in forming the binary representation of the number 581, namely 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, where the 1s represent powers of 2 that are present in the expansion, and the 0s represent those which are absent. It will be noticed that the exponents in this expression, namely the numbers 9, 6, 2, could also be represented in this way. 9 equals 2 to the power of 3 plus 1, 6 equals 2 to the power of 2 plus 2 to the power of 1, 2 equals 2 to the power of 1, and we get, recalling 2 to the power of 1 equals 2, 581 equals 2 squared to the power of 3 plus 1 plus 2 squared to the power of 2 plus 2 plus 2 squared plus 1. There is still an exponent at the next order, namely the 3, for which this representation can be adopted yet again. 3 equals 2 to the power of 1 plus 1, and we obtain 581 equals 2 squared to the power of 2 plus 1, 1 plus 2 squared to the power of 2 plus 2, plus 2 squared plus 1. For larger numbers, we might have to go to third or higher order exponents. We now apply a succession of simple operations to this expression, these alternating between a, increase the base by 1, b, subtract 1. The base referred to in a is just the number 2 in the expressions, but we can do similar things for larger bases, 3, 4, 5, 6, and so on. Let us see what happens when we apply a to the last expression for 581. So 2's become 3's. We get 3 to the power of 3 to the power of 3 plus 1 plus 1 plus 3 to the power of 3 to the power of 3 plus 3 plus 3 to the power of 3 plus 1, which is in fact a number of 40 digits when written out in the normal way, starting 1, 3, 3, 0, 2, 7, 9, 4, 6. Next, we apply b to obtain 3 to the power of 3 to the power of 3 plus 1 plus 1 plus 3 to the power of 3 to the power of 3 plus 3 plus 3 to the power of 3, which of course is still a number of 40 digits starting 1, 3, 3, 0, 2, 7, 9, 4, 6. Now apply a again to obtain 4 to the power of 4 to the power of 4 plus 1 plus 1 plus 4 to the power of 4 to the power of 4 plus 4 plus 4 to the power of 4, which is now a number of 618 digits, starting 1, 2, 9, 2, 6, 8, 0, 2. The operation b of subtracting 1 now yields 4 to the power of 4 to the power of 4 plus 1 plus 1 plus 4 to the power of 4 to the power of 4 plus 4 plus 3 times 4 to the power of 3 plus 3 times 4 squared plus 3 times 4 plus 3, where the 3's arise analogously to the 9's that occur in ordinary base 10 notation when we subtract 1 from 10,000 to obtain 9,999. The operation a then gives us 5 to the power of 5 to the power of 5 plus 1 plus 1 plus 5 to the power of 5 to the power of 5 plus 5 plus 3 times 5 to the power of 3 plus 3 times 5 squared plus 3 times 5 plus 3, which has 10,923 digits and starts off 1274. Note that the coefficients 3 that appear here are necessarily all less than the base, now 5, and are unaffected by the increase in the base. Applying b again, we get 5 to the power of 5 to the power of 5 plus 1 plus 1 plus 5 to the power of 5 to the power of 5 plus 5 plus 3 times 5 to the power of 3 plus 3 times 5 squared plus 3 times 5 plus 2. And we are to continue this alternation a, b, a, b, a, b as far as we can. The numbers appear to be ever increasing, and it would be natural to suppose that this will continue indefinitely. However, this is not so, for Goodstein's remarkable theorem tells us that no matter what positive whole number we start with, here 581, we always eventually end up with 0. This seems extraordinary, but it is in fact true, and to get a feeling for this fact, I would recommend that one try it, starting first with 3, where we have 3 equals 2 to the power of 1 plus 1, so our sequence gives 3, 4, 3, 4, 3, 2, 1, 0. But then more importantly, trying 4, where we have 4 equals 2 to the power of 2, So we get a sequence that starts tamely enough with 4, 27, 26, 42, 41, 61, 60, 84, but which reaches a number with 121,210,695 digits before decreasing finally to 0. What is rather more extraordinary is that Goodstein's theorem is actually a Gödel theorem for that procedure that we learn at school called mathematical induction, as was shown by L.A.S. Kirby and J.B. Paris. Recall that mathematical induction provides a way of proving that some mathematical statement, S open parenthesis n close parenthesis, holds for all n equals 1, 2, 3, 4, 5, and so on. The procedure is to show first that it holds for n equals 1, and then to show that if it holds for n, then it must also hold for n plus 1. What Kirby and Paris demonstrated was, in effect, that if P stands for the procedure of mathematical induction, then we can take G open parenthesis P close parenthesis to be Goodstein's theorem. This tells us that if we believe the procedure of mathematical induction to be trustworthy, which is hardly a doubtful assumption, then we must also believe in the truth of Goodstein's theorem, despite the fact that it is not provable by mathematical induction alone. The unprovability in this sense of Goodstein's theorem certainly does not stop us from seeing that it is in fact true. Our insights enable us to transcend the limited procedures of proof that we had allowed ourselves previously. In fact, the way that Goodstein himself proved his theorem was to use an instance of what is called transfinite induction. In the present context, this provides a way of organizing an intuition that can be directly obtained by familiarizing oneself with the reason that Goodstein's theorem is in fact true. This intuition can be largely obtained by examining a number of individual cases of Goodstein's theorem. What happens is that the modest little operation, B, relentlessly chips away until the towers of exponents eventually tumble away, one by one, until none is left, even though this takes an incredibly large number of steps. What all this shows is that the quality of understanding is not something that can ever be encapsulated in a set of rules. Moreover, understanding is a quality that depends upon our awareness, so whatever it is that is responsible for conscious awareness seems to be coming essentially into play when understanding is present. Thus, our awareness seems to be something that involves elements that cannot be encapsulated in computational rules of any kind. There are indeed very strong reasons to believe that it is an essentially non-computational process. The possible loopholes to this conclusion are that our capacity for mathematical understanding might be the result of some calculational procedure that is unknowable because of its complication, or not unknowable, but not knowably correct, or inaccurate, but only approximately correct. In relation to such possibilities, we must consider how such a computational procedure might come about. In Shadows of the Mind, I addressed all these possible loopholes in considerable detail, and I would recommend that discussion, and also the psyche account beyond the doubting of a shadow, to anyone interested in following up these issues more fully. If we accept that there is indeed something outside purely computational procedures in our capacity for understanding, and therefore in our conscious actions more generally, then the next step would be to seek where, in physical actions, any essentially non-computational behavior might be found. This is assuming that we also accept that physical action of some kind is where we must look in order to find the origin of conscious phenomena. I try to make the case that there is indeed nowhere within our present-day accepted physical theories where appropriate non-computational action takes place. Hence, we must look for a relevant place where there is an important gap in our theories. This gap, I claim, lies in the bridge between the submicroscopic world, where quantum physics holds sway, and the macro world of our more direct experiences, where classical physics works so well. An important point has to be made here. The term non-computational refers to specific types of mathematical action of the kind that has been mathematically proved to be outside the scope of computation. Part of the aim of this book is to bring such things to the attention of listeners unfamiliar with these matters. Non-computable processes can be completely deterministic. This is something of a fundamentally different character from the complete randomness that features in our present-day interpretation of quantum mechanics when a small-scale quantum effect is magnified to the classical level, the procedure referred to as R in the present work. I argue that a new theory will indeed be needed in order to make coherent sense of the reality that underlies the stopgap R procedure that we use in present-day quantum mechanics, and I try to argue that it is in this undiscovered new theory that the required non-computability will be found. I also argue that this missing theory is the same as the missing link between quantum theory and Einstein's general relativity. The term used in conventional physics for this unified scheme is quantum gravity. However, most practitioners in this field tend to assume that the rules of quantum mechanics will not be altered in the bringing together of these two great 20th century theories, and that it is only general relativity that will be subject to change. My view is different, since I take the view that the procedures of quantum mechanics, in particular the R procedure, must also be fundamentally modified. I use the term correct quantum gravity, or CQG, in this book for this undiscovered unification. But this would not really be a quantum gravity theory in the ordinary sense, and perhaps CQG is an unfortunate term which may have misled some people. Although this theory is still missing, this does not stop us from trying to estimate the level at which it should become relevant. In this book I refer to what I call the one graviton criterion. For some years now I have shifted my view away from this, and a far more plausible scheme, in my opinion, is put forward in Shadows of the Mind. This new scheme is not only more plausible physically and has an additional justification that I have presented in a paper, but it is much more usable than the previous scheme, and it has directed our thoughts towards new theoretical developments. In fact, there are now some physically realizable experiments for testing this scheme, which I hope can be performed in the next several years. Even if all this works out in the way that I am arguing for, it does not directly assist us in understanding the seat of consciousness. One of the major shortcomings of this book is perhaps that when I wrote it, I knew of no place in the brain where it could be plausibly argued that the large-scale quantum coherence could take place that would be needed for the application of the ideas that I have just been describing. But perhaps one of the book's strengths was that it found a broad audience amongst scientists who could contribute back to the development of our understandings in these matters. One of these scientists was Stuart Hameroff, who acquainted me with the cell's cytoskeleton and its microtubules, structures of which I had been deplorably ignorant previously. He also informed me of his own ingenious ideas concerning a possible role for microtubules within the brain's neurons in relation to the phenomenon of consciousness. It seemed to me that the most plausible place for the kind of large-scale quantum coherent action that my arguments required was indeed within microtubules. Of course, this information came too late for inclusion in this book, but it is featured in Shadows of the Mind and has been developed further in a number of articles, for the most part jointly with Stuart Hameroff. Apart from the new developments that I have referred to in this new introduction, the essential ideas of the Emperor's New Mind are the same as they were 10 years ago. I hope that the listener will gain some genuine enjoyment as well as stimulation from what I have to say. Roger Penrose. Prologue. There was a great gathering in the grand auditorium marking the initiation of the new ultronic computer. President Apollo had just finished his opening speech. He was glad of that. He did not much care for such occasions and knew nothing of computers save the fact that this one was going to gain him a great deal of time. He had been assured by the manufacturers that, amongst its many duties, it would be able to take over all those awkward decisions of state that he found so irksome. It had better do so, considering the amount of treasury gold that he had spent on it. He looked forward to being able to enjoy many long hours playing golf on his magnificent private golf course, one of the few remaining sizable green areas left in his tiny country. Adam felt privileged to be among those attending this opening ceremony. He sat in the third row. 2 rows in front of him was his mother, a chief technocrat involved in Ultronics design. His father, as it happened, was also there, uninvited, at the back of the hall, and now completely surrounded by security guards. At the last minute, Adam's father had tried to blow up the computer. He had assigned himself this duty as the self-styled chair spirit of a small group of fringe activists, the Grand Council for Psychic Consciousness. Of course, he and all his explosives had been spotted at once by numerous electronic and chemical sensing devices. As a small part of his punishment, he would have to witness the turning-on ceremony. Adam had little feeling for either parent. Perhaps such feelings were not necessary for him. For all of his 13 years, he had been brought up in great material luxury, almost entirely by computers. He could have anything he wished for, merely at the touch of a button. Food, drink, companionship, and entertainment and also education whenever he felt the need, always illustrated by appealing and colourful graphic displays. His mother's position had made all this possible.
Sample complete. Ready to continue?